start recording. And no power went. All right, everybody. Nice to see you all. I hope you had a relaxing Tuesday off, and you know, I appreciate those of you who are still here. I was starting late. Once again, our classroom was left a mess, and the class before us left 5 to 10 minutes late. But now we will get started, and I will share my thoughts with the university later. So let's see. In terms of assorted logistical stuff, hopefully we have all started and most likely completed homework 1. So I was watching on Canvas, and it looked like there was something submitted, which is fantastic. Our goal is to post homework 2 by the end of the day today or tomorrow. Not sure if Thea is aware of that, but that'll be our goal. I think it's basically already there. My goal is to not post the solution this time. And we will see if I manage to accomplish that. Other than that, so remember this class is on just a very simple cadence. Oh, and I'll try to post some more reading suggestions as well. You know, so just every week you put the engagement activity up, you turn in your homework every other week, and you have the project. So don't forget, you know, take another look at the project instructions, and all the deadlines and things that you need are on there. A few of you have already come to my office with ideas and just like things you might want to look at. It's still early, but that's fantastic, and I'm always happy to chat. Any logistical questions, concerns? No? Favorite like dad jokes? Interesting news items? Ah, you kill me. Okay, so today we are going to move from 1 dimension to 2. That's our goal for the day. And in particular, we spent all of last week talking about curves, which we thought of as 1-dimensional objects, even though they might have been embedded in some higher dimensional space, like 2 or 3. Today, we're going to talk about surfaces, and it's largely going to be a lot of overlap. So we're going to have a compressed discussion today in terms of like how to define what a surface is, and so on, because you'll see that there's a lot of commonality with what we've already done. And of course, the course notes also go through all of this in quite some detail. Anna was quick to point out in my office hours that the course notes actually had the solution to one of your homework problems. So if you're not reading the course notes, that's your bad. You know, you just lost points on your homework basically, unless you wasted a bunch of time. There you go. Yeah, see, that's on you. We'll go through the main points from there. And then we'll spend the second half talking about different discrete representations of surfaces. So this is a little bit flipped over from last week, right? Last week we had one lecture that was all smooth, and the next one was all discrete. Here we're going to talk about kind of smooth discrete data structures / definitions, like what we're working with. And then we're going to need more than one lecture to do essentially curvature, which will be our main goal, right? Like how do we quantify how much a surface bends through? So that'll be, I think, Tuesday and Thursday of next week, if not more, because I tend to talk too much. Okay, any questions about our plan? Ideas, directions, concepts? Yes. Okay. So our goal for today, at least superficially, is very straightforward, right? We're just going to take what we did last time and bump every 1 into a 2 and see what happens. Like we had 1-dimensional objects, which are curves. Now we're going to do 2-dimensional objects, which are surfaces, or 2D sub-manifolds of R3 will be our main objects. And really, in some sense, this is the biggest, I don't know, conceptual leap that happens. I mean, I think a lot of the math that we do for curves is super interesting, but very specific to curves. So like once we start working with surfaces, we're going to have to make a bunch of definitions and do all kinds of new math because surfaces are weird objects. But then from bumping from 2D to like 3D, at least for sort of beginner level differential geometry, that transition isn't quite so painful. So really this is the main conceptual leap. And there's actually kind of important theoretical reason for that. One big theme of our discussion when we talk about surfaces is going to be the difference between intrinsic and extrinsic measurements. And this is a term you might have heard before, right? So intrinsic is going to be like all of the stuff that like an ant could measure walking along the surface with no knowledge of the space around it, right? Like all it can do is basically compute distances by like, I don't know, do ants have string? If it has a piece of string and they can drag it along the surface, they can right? Whereas extrinsic geometry is going to have to do with how the surface interacts with the space around it. So here's a good example. Here are my scribbles for today's lecture, which I conveniently did in the last 10 minutes. From the ant's perspective, if I take this sheet of paper and I bend it, it's still the same sheet of paper. They actually can't sense that motion, right? Because distances along the surface haven't changed. So that has to do with the interaction between the surface and outside space, right? In some sense, origami is some version of that. Whereas, like, the difference between this thing and this bottle of Germ-X here, they're very different, and the ant can sense that because there's curvature along the surface, right? And so our big goal eventually in differential geometry here will be to, I'm not going to say prove, but motivate a theorem by Gauss, which is sort of the analog of what we did for curves, right? Remember we showed that if you know the curvature of a curve, you kind of know everything about it. The question is, what do we need to know to reconstruct the surface in 3D, A, and B, what do we have to know to reconstruct all the intrinsic structure of the surface? And we'll find that those are two different things. Namely, this is the difference between something called Gaussian curvature and something called mean curvature. Yeah? Plus a bunch of integrability conditions that we won't have time to get into, sadly. Okay, so that's our goal. So today we'll be talking about, like, how does one go about defining a surface? And you'll see that our definition, in some sense, I reverse engineered our definition of a curve in this class to suit the definition of a surface that we'll have now. We'll see that they're very similar. And then we're going to talk about how one might represent a surface on a computer. And the main structure we'll talk about here is the triangle, which is sort of the main one that happens in the sort of application areas that we'll consider in this course. Okay, and really, you know, eventually we'll also mention, you know, stepping from like two-dimensional objects like surfaces to n-dimensional ones. And I do think, at least on the sort of definitional level, that leap of faith is a little less complicated to make than from 1D to 2D. Oh, I actually forgot to finish my story. So we talk about difference between intrinsic and extrinsic geometry on surfaces a lot. What is the intrinsic geometry of a curve? It's just it's like a line, right? It's a straight, it's just a length, yeah? And so in some sense, the reason why curve math looks so different for most of the rest of this course is that curve math is all about how the curve interacts with the space around it. And in some sense, differential geometry goes out of its way to try and figure out what you can do without knowing about space, which I think is a difference that differential geometry books often don't call out, right? I mean, you read this first chapter on curves, it seems really pretty, and then you never use it again. and there's a reason for that. Of course, this is facetious. A lot of the constructions we do still will appear, but we're going to have to be a lot more careful. Okay, so again, today, and largely in this class, because, you know, we're concerned with computational application, and the majority, although not all of them, tend to involve embedded geometry, right? So we're really going to work with surfaces in the intuitional sense of, like, you know, a 2D slice of 3D space. In fancy Riemannian geometry, you might try to divorce yourself from that idea. Like, remember in lecture 1, we talked a bit about, like, looking at a map of the world splayed out on, like, this board here. Obviously, you know, there's a difference between the geometry of the geometry of the world, and you might want to try and separate those two things. But for the most part, we're not going to worry about that for now. We're going to just think of a surface as really like an object sitting in space, and the geometry is inherited from the space around it. Does that make sense? Whereas the map, that's not the case, right? You need to define a geometry on the map in order to measure things in, like, miles instead of inches. Cool. Ah, you guys are nodding. This is fantastic. You're still awake. Okay, so remember when we started 2 lectures ago, our first question that we asked was just, what is a curve exactly? Yeah, and remember we kind of went through a list of notions from calculus that we thought might define a curve, and we realized that most of them don't. Right? So as a reminder, you know, probably the way you thought about a curve in calculus was just as a function of one variable, but there are a lot of degeneracies that can happen, right? Like that function might have a zero derivative, in which case it's not a curve, it's like more like a cusp or a point. And moreover, you could have multiple functions that trace out the same curve. And our basic takeaway, as a reminder, was that a curve is not a function, it's like a set of points that can be described with a function, yeah? And that like kind of difference sounds pedantic, but it actually is going to be really important, and it made a lot of, what was I going to say? It really affected the way that we do our calculations, right? When we talked about computing quantities like curvature, we wanted to make sure we could attach curvature to the geometric object rather than the function. We had to check invariance to reparametrization, right? Namely, if I trace out this curve 2 different ways, I get the same quantity. Yeah? Okay. So, of course, I'm going to try and do the same thing in 2D now, right? Or like maps of the plane into 3D, really. And so, well, up here would be to think about maybe objects similar to parametric curves. We consider objects like parametric surfaces, right? So what is a parametric surface? Well, again, you know, we can go through exactly the same story that we had last week, right? You know, it's in some sense a function of two variables, right? This is a map from like, usually graphic on the left side uv and the right side xyz. I think that's reasonable. And of course, the picture we all draw is this one, but unsurprisingly, given what we talked about in our previous lecture, there are a lot of degeneracies that can happen if we just consider differentiable functions f, right? So in fact, one thing that I did is I just borrowed from our lecture and showed you very easily extend them into 3D. If nothing else, you could just kind of take any of the 2D counterexamples we had 2 lectures ago and just kind of drag them along a curve and now have a degenerate surface, right? So here's some examples here. So for example, what is the object here? This is a function of u and v, and the right hand side is u squared and cosine of u. So what do we notice about this function? Does this, gosh, you're killing me. Does this function contain a v in it? Letizia, is there a v in the first line here on the right-hand side? No, there is no v, only u's. So what is this object? Is it a surface? And we're shaking our head. What is it? Curve. Thank you. Put me out of my misery here. Okay. How about the second one? F of uv is 0, 0, 0. What is this object? On 3. 1, 2, 3. A little bit louder this time. 1, 2, 3. Thank you. Okay. And finally, the third guy. What is it? Well, I've plotted it here. It's sort of a cuspy-looking thing. In fact, all I did is I took sort of exactly the cuspy curve we had before, and I just stuck u in the first coordinate. So it kind of took that curve and dragged it along. Yeah? So I think we all agree that these are not smooth surfaces. The first two are not even surfaces. The third one is not smooth. But notice that all 3 of these are differentiable functions. Clearly, you know, once again, just like our 2 lectures ago, we went into some problems. Whew. Okay, so how do we address this? Like what do we do for curves? Remember, we said for one thing to trace out a curve, we need a function. And maybe we're only going to deal with differentiable curves. What condition do we need on that? Tracing out the curve to make sure that the degeneracies. You know the answer, so I'll stand here until someone raises their hand. Yes?
It was something like locally the curve looks like R1.
Locally the curve looks like R1. In particular, if I trace it with a function, what's the condition of the function? The derivative of the function has to be non-zero, right? So like if I'm a car driving along this curve, I never have to grind to a halt and then pivot and keep driving, right? I never have to do that. Incidentally, one technicality from previous lecture, there may exist functions that out that curve that grind to a halt and keep going. That's okay. It's just that there exists at least one that doesn't. Does everybody understand that? You guys are awfully quiet today. I'm dying up here. Okay. So, what does this suggest that we have to do? Ah, yes. Just the first. And you used exactly the right word. To the question I didn't ask yet. So, what are we going to do for surfaces? Well, now the derivative, remember, map of a function. So we have like, oops, I got my script. Function that goes from u, maybe you have a point here. Remember, we get this f. And we're in 3D. You can do 3 things. Z, right? Like that. So it's the only surface I know how to draw. So that's what we're going to be looking at a lot of that the coming couple of weeks. Oh, there's another one too. That one. See, it's the donut. Okay. Right. So let's see here. So we now have some point over here, f of p. And in some sense, we can think about our previous definition of a curve as like what? The curve needs to kind of have a well-defined tangent vector. In some sense, that's what that non-degeneracy condition is saying. You know? So now our colleague here has mentioned that we've got a Jacobian matrix. And you know, we need to think about exactly what the Jacobian matrix is doing, right? Like this is an analogy of differentiating f. Yeah? So remember, the Jacobian we defined as this matrix of every possible derivative of f with respect to every possible input. That's things. But now let's draw a little bit of a picture just to remind you of how I might use Jacobian of f. Namely, I can draw a little tangent plane for my surface. And so like if I wanted to locally approximate my surface up to second order, I guess, what could I do? Well, I could do to approximate, for example, maybe f at some point q. And what would I do? I say, well, that's f of p plus, and then what would be the next term in my Taylor series? I know you're computer science students, so it takes a minute to page this to main memory. Yes? That's right, thank you. So it'll be df evaluated at p multiplied by q minus p. Thank you for correcting. Okay, just like that. Plus some other stuff. So, you know, in usual lazy math notation, we might do this. Yeah? Okay, so if I slice out this term, then really what I've done is approximate my surface with a little plane, yeah? And so what condition does that suggest on df? Because like essentially, remember that like in some sense, how could I think? Well, remember what little curve I draw through f of p, I need to degenerate, just like, you know, our previous one. Yeah.
Must be full rank.
Must be full rank. Okay. Thank you. So I can now advance. Right. So in other words, what does that mean? That sort of I can't take the directional derivative of f and 0 is an equivalent. You have to be a little bit careful with the full rank term because what is the size of df? How many rows? Like think about the output here. Yeah, it's 3 by 2, right? So it doesn't make sense to say invertible here, but it is full rank, meaning that like, you know, it can't have rank 1, meaning that everything collapses to a line. Yeah. Any questions about our sort of definition of a parametric surface? Notice that I've flipped over our discussion from previous one, right? So here, if I want a function f to trace out a surface, well, I can almost do that, but I do need that f doesn't have degeneracies, and the way that I prevent that is by looking at df at every possible p and making sure it has rank, specifically rank 2 here. Yeah? And then obviously in higher dimensions, it would be rank of the dimension of the object. Yes?
So here you're talking about a local parameterization.
And we're not talking, this is just like a little patch. If I want to trace out a patch with function f. They know I've swapped my discussion from 2 lectures ago where we started with a curve and then did parametrized curve. Yeah. Any other questions? It's a good question. Cool. Okay. So that's a parametric surface, and that's a good place to start, right? But of course, parametric surfaces aren't really what we want to work with, and this is even more the case in surfaces than in curves, because the reality is that like every differentiable curve is a parametric curve up to like connectivity, you know, as somebody pointed out after lecture the other day, which is my bad. But here, for example, if I have this very complicated triple torus object here, cooking up a function f that traces out this entire thing is difficult, if not impossible. Yeah, I guess you have to be careful saying impossible because if you are allowed to double back on yourself a few times, you might be able to do something weird. But certainly, it would not be a very convenient representation to think of every possible surface as the image of a single map f. Just the same way that, like for curves, we want to think of a curve as a set of points rather than like a function. Yep. Cool. All right. So what are we really going to do? Well, if you remember, we had this nice. Uh-oh, it blinked. We have this nice schematic. Oh, that actually reminds me. I don't think I turned on the recording. By you people. Oh no, I did. Huh. I'm good at this. Okay. So if you recall, maybe why is PowerPoint not doing what I'm telling it to? The laptop has finally hit the limit. It's just had enough. Okay. So if you recall the definition of a curve, remember that we started by saying, well, if a curve is a geometric object, we should say like the first kind of chunk of my definition would be a curve is a set of points with the following property, right? Rather than like a curve is a map from R1, right? So we want to do something, and remember how we did curves. We said, okay, a curve is a set of points with the property that if I take any point, I can like cut out a little piece of the curve around that point and parameterize it with one of these non-degenerate functions, right? That was our definition before. So what are we going to do? Well, just like for curves, for a surface, essentially we're going to have a very similar kind of structure, but now it's just that our function is a function from R2 to R3 rather than a function from R1. Yeah? And we already have our non-degeneracy condition kind of written down here. Well, not written down. D, F, rank 2. Now it's written down. Okay, but it'll be a slide. So in particular, we're going to say that a surface is an m-dimensional. Oh, oops, wait. Did I have the surface definition in the slide? I feel like I deleted that slide by accident. All right, well, let's do the slightly more general case, which is not just a surface, but an object called a manifold. Sorry, I forgot my story for a minute. Which is sort of the m-dimensional analogy of a surface. Right? So a surface would be like a 2-dimensional object. A curve would be like a 1-dimensional object. A volume would be a 3-dimensional object. Beyond that, I think we kind of lack words. So in general, we can talk about a submanifold of Rn with and without boundary. So we're going to talk about boundaries in a second, right? So like for a surface, maybe like this little set of points here doesn't look like a map of R2. That's necessarily not. Right, and so it has the property that for every p, there exists 2 open sets u and w and a function g, so that our function is smooth and like injective onto the surface and has that rank condition. So let me draw a picture of what this looks like. It's also on the board, but I think it helps you to kind of talk through it a little bit. So I've got my own little picture down here. So first of all, just keeping score, in this class, we're going to try and be consistent with some notation, which means that inevitably in about 2 minutes, I'm going to get it wrong. But in particular, let's think about a curve on the plane. And there's 2 numbers here, m, which is the intrinsic dimension, and n, which is the extrinsic dimension. Yeah? Like what would for a curve in the plane, what would be m here? 1. Say it louder.
1.
Thank you. 1. And what would be n, the extrinsic dimension for my curve? 2. 2. Okay. Right. Similarly, let's say that I have a surface and it's sitting in 3D. There's my surface. See, I drew it again. So what is the intrinsic dimension of my surface? 2. It's 10. And what is the extrinsic dimension? 3. Yeah. And finally, let's say I have a curve and it's sitting in 3D. So what's the intrinsic dimension? 1. What's the extrinsic dimension? 3. So all these objects are manifolds, right? They're just different traces of m and n. Okay, so now let's go through our definition a little more slowly because it's enough to think about. Okay, so let's not worry about the boundary case for now. We'll come back to that in a moment. Yes? That's a fantastic question. So the question was the difference between a manifold and a submanifold. So in this class, we're mostly going to work just with submanifolds, and that means that it is sitting in Rn. I was thinking n. So in general, like think about that map example, right? This is what I'm going to keep going back to. You probably wouldn't want to think of that as like an embedded submanifold of the plane, because that's like, it's not really inheriting the geometry of the plane. There's a slightly more generic notion called manifold, where you want to not necessarily think of it as even sitting in a space. It's like just a topological object. So it's just like a set of points with some connectivity defined on it. That's sort of out of the scope of this class to define carefully, because then you like don't even have calculus at your disposal doing some work. But it's not so hard. Like if you dig up your favorite like DeCarmo definition, you'll find it's kind of reasonable extension of what we're doing here. Yeah. In fact, I think it's in the course notes. Right. So if we go through our sort of picture here. So now let's say I have a manifold with boundary sitting in R3 again. Okay. So what is this definition saying? It's saying that I can take any point. And its name is M for manifold, or Matthew. Okay. So I have a point on my manifold, and in our definition, we call that point P, right? And then what is it saying? It's saying that there's some map into a neighborhood around P, but we have to be a little bit careful what that means, right? So here's all the conditions that we're going to put on our map. We're going to say that there's open sets U and W, and essentially we're going to think of W as like the source of my map, and U as the target, right? And what do I want? Well, essentially I need this little parametrization, which we call G. And then essentially what goes on in this definition, although I always forget why we need every single one of these conditions, so and I know you're about to ask me that, and I'm going to get it wrong. Every year I forget to look up the picture so I can put it on my notes, but we'll come back to that. Essentially what we want is for G to be an invertible map onto its image, right? Meaning that like the map from this little patch to this little patch doesn't over on itself, something like that. And moreover, that it admits this rank M condition, right? So here it's rank M instead of rank 2. Immediately Rm. It's just hard to draw for anything bigger than 2. That was an M. Okay. All right, so it's really exactly the same picture that we had before. A surface is a set of points with a property that I can choose a point here, and then I play this little game that I need to be able to parameterize that patch. And the way that I do it is I draw a little blob around this point, a little blob around a source point back here, and that this map is non-degenerate. But we have an added headache here, which is that we want our surface to have a boundary. So here, a boundary is like, you know, the outer thing of this patch. In this course, we're going to assume we have a smooth boundary. So secretly, this picture kind of looks like that. Otherwise, you have to for like a little angle, and we don't want to worry about that. So at if I take a point along the boundary, let's say this guy, and I take an open around it, does that set look like the image of an open set in the plane anymore? See head shaking, yeah, right? Because essentially it's like kind of okay over here. At this point, of course, there's nothing underneath it, right? And that's a problem because I have this nice smooth function here. So what do we do in that case? We just chop it off. So we say, okay, if I want to parametrize my function over here, then rather than being a map of a set in the plane, will be a map of the set in the plane intersected with the upper half plane. So like we only consider the upper half part of this thing, right? And then at any point which is along this line here, we will consider to be the boundary of our surface. Does that make sense? So we kind of have two. You have a choose your own adventure as to choose your parameterization. There are two options. Secretly the same option because I could have put my set like up here, and then there wouldn't be a boundary, right? Okay. Any questions about that definition? It's a little finicky. Yes.
What if the surface is like a closed boundary all around disconnected, and then you map it to 2?
Mm-hmm.
Was it working? It's not like connected.
Yeah. So the question was like, okay, let's say I have. Oh, you're gonna make me draw this? Let's say that I have a surface, which is the upper half of a sphere. Okay. I'm really proud of my dotted line. You know, this boundary curve here, which is this thing, it maps to S1, right? It maps to a circle. But that somehow feels contradictory to this definition because, you know, there's no circle here, it's a line. And the reason that that's okay is this is a local definition. It just says that around every point, there exists some small patch that is the image of an open set in R2. It doesn't say that the whole surface is the image of one function. Yeah. Cool. Uh-huh.
Why do we need the additional stipulation that the continuous shouldn't the Jacobian?
I believe that may be the case. I was wrong. I think there actually is a reason to put that book, and I knew you were going to ask that question. Every year I forget to check whether there's a reason I put it there and I forgot. If you remind me after class, we will Google it and figure out. Yeah. Sorry. It is a 100% reasonable question and one that your instructor should be better prepared to answer. But essentially, it's to find morphism, but I forget if the rank condition ends up being redundant. I don't think it does for like a stupid technical reason, like a certain type of cusp, but I'll have to think about it. That's my apologies. Yeah.
This is a little different from the definition of manifolds, like math books, because it's ignoring kind of the smooth structure. Because you can, you know, in the sense that the family of functions G and their domains can be different for the same surface.
The family of functions of G and their domain.
Right. The charts that you pick, for instance, like the four-dimensional sphere has multiple smooth structures that are not the same. For curves, you said that this definition coincides. The curve definition that you gave that also didn't talk about specifically the smooth structure. Coincided with the family. I guess that made sense to me because the curve can be embedded in like a dimensional you go to higher dimensions, even like R4 doesn't admit a single manifold structure. There's the exotic R4 smooth structure on R.
This feels like more of a comment than a question. Right, where are we going?
Given that we're ignoring the specific kind of smooth structure that we're thinking about, will this coincide with the definition? Take that as part of the definition, or?
Why don't we save this discussion another time? I mean, I think this definition is perfectly fine, partially because I brought it from a differential geometry. That's what at least my textbook agrees. But I think essentially this is the undergrad version. We have geometry and it is specifically inherited from Rm. If you put some other geometry on the space and you talk about submanifold more generically, then yeah, I don't know, you might need some more condition. I'd have to check. Sorry, I don't know offhand. Geometry professor, I know. Any other things I can, sarcastically ignore? No, really. It's a reasonable question, but for this course, this is a very concrete notion, and I think that really isn't going to matter a whole lot. There are some undergrad differential geometry types that do define surfaces as a collection of coordinate charts, right? And that's closer to how you might go about defining a manifold, because you could imagine then you have some space, you have a bunch of maps into that space so rather than thinking of there being like a well-defined map into this object, you might instead say for any two maps into this object, you kind of compose one with the inverse of the other and talk about properties of that composition. That's sort of better topological definition. It's a little harder to grasp and kind of unnecessary in this context, but that would allow you to put more interesting geometry. But then still, if you go to the definition of submanifold, which is what we're calling this object, it ends up looking very similar. Yeah. But I hesitate to claim that they're the same because I know the second I do, you're going to tell me I'm wrong. Give me a hard time. All right, any other questions? This definition is totally reasonable as long as you don't think about it too hard. Yeah, okay, fantastic. So essentially, really what this phrase is just telling us is that a surface is a locally planar object. We have to be the tiniest bit careful what we mean by planar, yeah? Okay, we're going to continue making some more definitions. So the first one that we're going to do is to think about the image of this Taylor series up here, right? So if we just chopped it off into two terms, then we get a plane that just barely touches the surface right at the point, I guess, f of p here, right? And what do we call that plane? Tangent plane. Thank you. Thank you. Okay. The object is the tangent plane. There are many definitions that are equivalent for tangent plane. At least I think they're equivalent. So essentially, I think the one that you usually encounter, for example, in the textbook, looks like something like this, which is the tangent plane. I kind of like this definition because it's a very geometric feeling, but then it's totally inconvenient. So we always go back to this for real life things, which is that the tangent plane is sort of the tangent to any curve that passes my point, right? So the collection of all of those tangents, right? So like, I have my point P on my surface here. Now I can draw any curve, for the previous lecture that has its own degeneracies. And let's say that my curve specifically is along the surface, so it can't leave this 3D object, 2D object. Well then, what I can do is I can say, okay, for any curve, that curve has a tangent, not necessarily a unit tangent, just a tangent. And if I look at the collection of all those tangents, they form a plane. And that plane is a tangent plane. So geometrically, that feels like a very nice thing. Practically, it's kind of annoying. So what we argue is that that's basically the image of df, right? How do I go about arguing that? Well, if I have a curve that is actually along the surface, well, what can I do? Let's say I have a local parametrization. Conveniently, I do. His name is G, or her name, whatever. And I write, well, if I can write a curve along the surface, then I can sort of express it as G of a curve down here, at least locally, right? Of maybe gamma of t, like that. So if I apply the chain rule, right, I differentiate this with respect to t to get this definition here, what am I going to end up with? I'm going to end up with the Jacobian of t times gamma prime. And so that's how I can go about arguing that definition is much easier, or is basically equivalent to like the image of df. Yeah. By the way, there's a slight technical difference when you think of the tangent plane as going through P, or a slightly basically equivalent object, which is a tangent space, which is just the image of df, right? So that would do like recentering at the object. Okay. So right, so here's yet another way to put it in case we didn't, we want some more notation. There's two equivalent notions. Either the set of, really there should be like sets notation around that gamma prime. My apologies. Or we can say it's the image of G, right, where G is a local parametrization about our point. But then we have to be a little bit careful. There's this annoying DG inverse because I have to kind of figure out where did what point mapped to P, right? Okay. So have I managed to confuse you yet about the tangent space of the surface? At the end of the day, it's I think of it as the image of Jacobian of our parametrization. Yes, you guys are very agreeable, except our one colleague here who's thinking critically. The rest of you, I don't know. Essentially, what's the problem here? I could have multiple G's that trace out a little chunk of my surface here. So what could go wrong? Like, let's say that I flipped my definition backward. Notice I sneakily did it the opposite way because I kind of proved something in an empty fashion, right? Let's say that I said that the tangent plane of my surface is the image of DG evaluated, the pre-image of this point. What would be that definition?
Seems like the image of G doesn't necessarily include the whole plane.
The image of DG will trace out a whole plane. That'll be okay, because we already know it's not that's part of definition of surface. But there's a different issue, which is that two different G's could trace out the same patch, right? So then I would have to prove a lemma that says if I chose two different G's and they both, trace out my surface, they both agree at P, then when I take DG, I get the same image, right? I have to prove a little theorem like that. Yeah? Notice, by virtue of starting with the definition of it is the collection of tangent vectors to curves along my surface, I kind of don't have to do that. In some sense, I've just reversed that proof, right? Like, well, one way to show that it's independent of G would be to show that it's equivalent to that first definition. Yeah? Okay. This is the kind of thing you have to ask every time you write a new formula in differential geometry. Like, if you start using coordinates like we did, like dg here, we have to be super careful to make sure that we didn't make something that's sensitive to my choice of G. That's my point. Cool. All right, so the next object we're going to define. So this is all, for those of you who are computer graphics or vision students, this is all a very familiar story. So we have the tangent plane surface, and then what's sort of dual to that, right? Like that's the 2D piece. And then what are the other objects? Often for rendering, for example. Yes? Normal vector. Not quite, but close. No, actually, I'm giving you a hard time. We're going to define something called normal space. So we have the tangent space as all the points on this plane. Now we're going to say, like, basically the orthogonal complement of that object, we're going to call normal space associated to my point P. I don't know if we're familiar with this little notation, this orthogonal complement, but just in case we're not. If I have a vector space V, look at its orthogonal complement, so this notation here. This is going to be like the set of all W, so that W dot product with V equals 0 for all V in vector space. In other words, it's like the set of all things that are orthogonal in the tangent plane. So like, if this is my plane, you can tell it's a plane, like the edges are straight lines. Then the normal space would be kind of like this line. Yeah? Okay? Now, Kurtik was anticipating something, right? Which is, he used the phrase normal vector, which would be like a single choice of vector, which is a unit length object in the normal space. But we actually usually try to start by just defining the normal space for a key reason, which in retrospect will be obvious, right? So in general, like if I have this sphere, right? This thing has a well-defined normal vector at every point. By the way, every surface that we've defined, or at least away from the boundary, even in the boundary, I guess, has a well-defined normal space. That's perfectly fine. It's like a one-dimensional set. And the surface, I can make a map from the surface to a normal vector, which actually this is not a great drawing because it'll also be the unit sphere, which tells you like at every point maybe a unit vector that points outward from that location. Yeah? So I can think of this, like I might think of this as actually a map from N here into like I'm going to write S2 even though that happens to be for this picture. Which is saying for every point on the surface, there's some unit normal vector that I could have written down. But why haven't I defined that object yet? Can I say every surface has such a function n? The Mobius strip. Thank you. So let's. Do we want to do a live demo? Do I need my notes? This paper is like a little too wide. Let's see if I can do it just. I'm gonna regret this later. There. Some of my equations are gonna be missing whatever the last symbol is. Okay, so let's say that I take a little strip of paper like this. If I join it together like that in a ring, this object very clearly has a normal direction at every point, yeah, like that. But if I take the end and I just twist it one time, and now I glue them together, I get a very special surface called the Mobius strip. Right? This is technically, I guess, a surface with boundary, the way I've drawn it, or realized it in space. What happens if I take the normal vector and I start sweeping it along the surface and I get back to the point I started? I encourage you to all try this at home. Yes?
It looks the opposite way.
Yeah. If I take this normal vector, I sweep it along the surface, just continuously, then by the time I get to the same point, I'm pointing inside instead of outside. You can kind of see that because in order to construct this surface, I had to flip things over once. Right? So there's clearly something wrong. So does such a function from the surface into the unisphere exist in this case? Not one that's continuous, right? At some point I've got to do that. Yeah. So that's why every surface, the way we've defined it, has a normal space at every point. But that's not the same thing as saying that there exists a function into the unisphere that gives the normal vector, unless you're willing to let that function have discontinuity. Now, I can always do that locally, right? I can like cut out a little patch and then make such a thing. But the existence of this function globally is a topological function. So we're going to make another function. We have surfaces, and we're going to have variable surfaces, which may exist. Ugh, this laptop is like really hating its life right now. So we're going to call an orientable submanifold. Specifically, by the way, normal vectors only make sense if the dimension of your manifold is one less than the dimension of the space that you're in. Right? Otherwise, the normal space is going to have more than one dimension in it. But specifically, if there exists a function, we'll call it n for normal, which is continuous is probably good enough, which takes every point and maps it to a normal vector, and that just exists on this object. We're going to call that an orientable surface or submanifold. Does that make sense? Mobius strips are examples of non-orientable things. Let's see. What's the famous non-orientable submanifold of R4? The Klein bottle. That's right. Yeah. So right. So most surfaces we'll deal with in the class will be orientable. Although actually the assumption won't matter a ton for some of the analysis that we're doing. Like a lot of the shape analysis is perfectly happy to have a non-orientable surface. Okay. Any questions so far? I think this idea is reasonable. These things are all easy to kind of jumble together, and we just have to be really careful. And you guys are keeping me honest about like what we need like in order to do certain calculations or constructions, right? Okay. Oh, by the way, I guess I did throw into the slides this more generic definition of a manifold without the space outside of it. I'm going to flip the slide before we start arguing about the details. Okay, so let's now move from the smooth world into discrete, essentially to transition from terracotta bunnies into triangulated ones here. And in this first part of the class, we're going to mainly focus on triangulated surfaces, specifically as a shape representation. There are many out there, right? Like these days, for example, in machine learning, it's very popular to use level set representation of a surface, namely these SDF objects. In other areas, maybe, I don't know, what are some other things? Point clouds is a popular one, and LiDAR, many different representations out there. Surfaces are nice because if we're going to try and construct this nice kind of discrete differential geometry theory, we'll see that it's very cleanly on a manifold triangle mesh, and not so cleanly on a lot of these other structures. In fact, I think it's sort of an open problem if you wanted a really consistent, beautiful theory on some of the representations. Okay, so actually, our main object of study for the next couple weeks, really, will be this particular object called a triangle mesh. How many of us have seen a triangle mesh before? Trick question, because you're looking at one. So you, with your hand down, I know better. Right, so a triangle mesh is just a big collection of triangles. Of course, we have to be a little bit careful. You know, triangle mesh, it's tempting to just definition, like to just make a definition like a triangle mesh is a set of triangles. But like, you know, having one triangle and then like a potato chip, like kind of stabbing into it would not be a very good triangle mesh. Well, this is probably fine, but like maybe 3 triangles that share an edge is a little bit more worrisome. And so we need to be a little bit careful with our definition, just like we did before. Yeah? Okay, so essentially, what is a triangle mesh? There are many different ways to define that are equivalent to each other. If you know, crack open the Hatcher topology textbook, they have some very similar discussion. Here's one way to think about it. The triangle mesh you can think of as like a triplet of objects. There's vertices, edges, and faces. And essentially, you can think of vertices as a set of points, edges as a set of pairs of vertices, and triangles as a set of triplets of vertices. And then obviously there are a lot of conditions that link all of these things together, right? So for example, you know, for essentially every edge here needs to be contained within a face, right? And so on. And so the course notes go through all the different constructions you need. It's actually really annoying to do carefully. There are a lot of different conditions you need for manifoldness that we'll talk about here a bit. And the formal definitions I'll defer to the written notes because it's just annoying. It's one of these things that is quite intuitive, and most of the objects we model end up being nice manifold triangle meshes because it's hard not to. But actually kind of articulating all the conditions you need is something that's a little tricky. But let's see what we can do here. So first of all, notice that already our definition is a little bit different from surfaces in like 3D in the sense that we actually have 0, 1, and 2-dimensional objects all kind of glued together in this data structure, right? We have faces, edges, and vertices. And in some sense, for a simplicial complex or a triangle mesh, that's sort of needed because this is only like this piece of smooth object. You really do have these like facets and points that are special. And essentially, that's all we're doing to come out. Of course, sometimes people call them faces instead of triangles. Anybody have an idea why? Like we often say a triangle mesh is a collection, right? V, comma E, comma F. That feels weird because F is for triangle.
You could have a mesh that is made of more polygons, and when you actually render it, you simplify it down to triangles. But having like quads can be better for polygons.
That's true. We could replace triangles with other polygons, but just specifically, why do we make this weird original choice that the triangles are F? Yes.
The face has a direction.
So we don't have to worry about orientability quite yet. There's actually just a stupid reason we're thinking about it. Yes.
Because we have to deal with tetrahedron.
The word tetrahedron also starts with T. So oftentimes, if you want to write software, you've got V, E, and F, and then you want to make it work for volume meshes. You have overloaded letter if you use T for triangle. That's all. You guys are all thinking far too critically. Okay. Right. So essentially, the issue comes that you get this messy data. Here's a nice example. This is actually collected from some sensor or another. Surfaces where, like, yeah, so this sounds so far, right? We had a collection of these edges and faces, and actually, there's some topological restriction here. Like, we don't have vertices floating in space that aren't touching a triangle, so something is satisfied. But will we consider this thing to be like a manifold surface without boundary, or like some analogy of that? Probably not. And even if you consider it to be a surface with boundary, in this case, the boundary would be the edge of every single one of these triangles, which probably isn't the notion that we're after. Yeah. So essentially, what we're saying, well, we're missing topology, which is like all the things that we can do on a shape that don't involve like local measurements that you need to have a ruler or a protractor, right? So topology is all about connectivity. Topology for discrete objects like meshes is a lot easier to think about and reason about, at least for me, than the smooth one, although both of them are quite annoying to do if you go far enough. All right. So for example, if you're not used to thinking about difference between geometry and topology, notice that all of our meshes are basically borrowed images from Wikipedia. This dolphin mesh, a geometric statement about this mesh might be something like this vertex is located at a particular position, whereas topology would be a statement about connectivity. So going through, if you want to do this really, really carefully, the definition, the Google phrase is looking for is you need an orientable combinatorial manifold, which is going to be a collection of simplices, right? So like a surface would have 0, 1, and 2 simplices, which are fancy is for points, edges, and triangles. Right? A tet mesh would then have, I guess, 3 simplices, which are tets. And there's like all these different conditions on how they connect together. We're not going to do the general definition in this class because it's just kind of out of the scope of our discussion here. But it is, I believe I made some, I did the old college try in the course notes and tried to write it down. So I'll let you guys check if I managed to get it right. Here's the kind of picture that we're trying to avoid. So essentially, we want to avoid things like this edge here. Notice that this is very clearly a non-manifold edge. There's like no equivalent to the object in the slide here. And similarly, like I don't want to be able to glue vertices to the midpoint of an edge or something like that, at least in the particular theory. Yeah. So luckily, triangle conditions for manifoldness are much easier than the more general case for simplicial classes. And in particular, they're here. That every edge is adjacent to 1 or 2 faces. So what would be a boundary edge? An edge that's adjacent to 1 face. Thank you. And every face incident to a vertex form this closed or open fan. Like namely, you can just enumerate them into a loop or into a line. And again, this has to do with whether a boundary vertex or an interior one. Yep. So these conditions turn out to be sufficient in 2D, and then in higher dimensions, it's just annoying. If you think about it, that makes sense, because you need to check the compatibility of like all of the tetrahedra with all the triangles, and all the triangles with all the edges, and all the edges with the tetrahedra. So like there's some conditions that skip a dimension that you don't have to worry about if you only have 2. Okay. Right. So this is enough of a definition for us, and since we're mostly going to be doing 2D math for the coming couple weeks, we'll stay here. Cool? All right. Notice, by the way, let's say that I forgot my geometry in this definition. So namely, I have, you can think of that data structure that I laid out as literally 3 arrays, right? Like an array of vertex position, array of edges, array of faces. Let's say I accidentally forgot the vertex positions. Could I do a condition just with the list of like triplets? You're nodding, right? This is yes. So this is a topological definition. It doesn't prevent cases like this. It's just worried about like not having a fan of edges or something like that, right? This is a purely connectivity-based definition of what it means to be manifold. Yeah. And for almost all the calculations we'll do here, that's actually perfectly fine. Even detecting that this happens on a triangulated surface is a difficult algorithmic question. Yeah, difficult-ish. Okay, difficult to do fast with an n squared. How about that? Okay, right. So in this class, we'll mostly assume our meshes are manifold, although I'll try to mention when you need that condition. There are some interesting research projects that try to that assumption, incidentally, and there are many ways why you might. So for example, fluid simulation is a good example of a domain that often tries to get around condition. Think about like simulating a bubble, right? Like the typical example is like you have 2 things, you know, like a bubble is connecting 2 circles to one another. You start pulling these circles apart. Then, as you might expect, the surface kind of bows inward, right? And eventually it forms basically a one-dimensional structure, right? And at some point it really like cuts off, right? And so in a lot of fluid simulation, you know, if I have a crown, meaning that like I drop fluid into a bucket and it forms this, right? Well, the bucket is a 3-dimensional thing. Maybe you have these like little 2-dimensional sheets of fluid that are coming out of it, and then like little spray points or lines coming off of that. So in that case, it's a good case for having this more general geometric object is non-manifold, because there's like pieces that are 1-dimensional, pieces that are 2-dimensional, something like that, right? A lot of the calculations we'll do here will compile on those objects, but won't make sense. So for example, you can take our definition of Laplacian operator, triangle mesh, and you can just kind of like make it work on these objects. It's just completely meaningless. So you have to be really careful about what you're doing there. There's a second reason that some applications violate this domain. So here is a very typical kind of image from computer design software, which is another typical application. Let's say that, now I'm terrible at CAD. I wish I were better at it, but I'm horrible at it. I have no spatial reasoning. It's shocking given my job and whatever. Let's say I want to make a table in CAD, and I'm using it in virtual reality. I'm not going to 3D print it. Then probably, you know, I'm going to take my table, and how could I, for example, model this guy? Well, it's got this, and it's got these 2 legs, which are cylindrical. So probably I would open AutoCAD and I'd get a rectangular surface and 2 cylinders, and I just kind of jam them in there and maybe push the cylinder a little bit past the bottom surface of the cube here, because then you won't see it. Is that thing going to have the right topology? Like, does it have the connectivity to the surface? No, it's like 3 disconnected objects, right? And so a lot of the data that you get out of CAD software looks right, but from like a manifold processing perspective is total garbage. This is actually a really big issue now that it's very popular to study machine learning on big geometry data sets. A lot of the data out there come from CAD because it's the easiest data to just go out there and find, that and LiDAR. And then you end up needing all this mesh processing software to process your data set before you can even study these mesh problems, because the data is just really messy, right? So like that ShapeNet data set that you may have encountered is a good example of that. Like the data that they drew from was these CAD models, and then there's this whole pipeline they had to implement that, turn it into like manifold surface. Okay, but essentially, if we're now dealing with mostly like smooth objects, we'll deal with some of these combinatorial objects later. Then essentially these piecewise linear faces, right, these triangles that we're building surfaces out of, are pretty reasonable building blocks for like a model of what it might mean to be a 2-dimensional surface on a computer. That's what we'll be working with a lot. And of course, there are many advantages to working with this data structure. For example, they're easy to render, like they're easy to draw on the screen. You can make arbitrary topology, meaning that it's like easy enough to form objects with holes in them and boundaries and so on. And they're also the basis for a lot of other algorithms that make even nicer geometries. So for example, in computer graphics, it's very popular to find an object called a subdivision operator, which takes a triangle mesh and then makes a sort of denser one out of it, using that original mesh as like control points. And these sorts of procedures are really what a lot of people use for 3D modeling. Okay. However, it's worth noting that like not all meshes are created equal. And in fact, a lot of what we'll do in this course is going to be a question of robustness. We'll find that even if we can trace out the same object, our algorithms are going to behave very differently. So for example, here's a pair of meshes. Something like, you know, these are both meshes that square. In some sense, they're both expressing the same piece of geometry. What we're going to find as we start to do calculus or calculus-looking calculations on these two objects is that suddenly they're behaving very differently, right? Because somehow on the right-hand side, we have this basically uniform, not quite, but like uniform model, right? All the edges are kind of similar. The triangles look almost equilateral. Whereas on the left-hand side, like, okay, there's some giant triangles like these guys down here. There's some tiny ones on the side. The edges are all different lengths. We're going to find that some calculations on the left-hand side are going to be less successful on the right. And our definition so far hasn't really captured that, right? So it's like a thing to keep in the back of our heads. Here's one way to think about it. If I wanted to model a function like curvature on this object, right? Well, most likely what would I do? I'd think of associating one scalar value with like every vertex of this structure, right? But suddenly our degrees of freedom are sort of unevenly distributed on this square, and that's going to create some problem, right? It's going to be easier for me maybe to compute some quantities in the dense areas than the sparse ones. So mesh quality is a big consideration in practice. There are a lot of algorithms out there that try to extract really clean meshes, like the one we saw on the previous slide. We'll touch on those a little bit, although there's only so much we can do one semester. Okay. So let's return to our discussion of topology a little bit and introduce just a few more terms. Again, today's mostly definitions, and then starting next time, we will do Gaussian curvature, which is really the fun part. Right, so the first thing we can do is define which you may have seen in graph theory, called the valence of a vertex on a triangle mesh, right, which is just the number of edges that go out of that thing. And finally, there's one really weird quantity which you may have encountered. Actually, in high school geometry, you might have encountered with a polyhedron, where you take the total number of vertices minus the number of edges plus the number of faces. This thing gives you an object called the Euler characteristic. If I catch you pronouncing it, you get you like minus 10 in this course. You laugh, but you won't be laughing when you look at your grade sheet. Okay, so as much as I'd love to prove a very famous theorem in this domain, we simply don't have time, which is that the Euler characteristic for a surface without boundary, a manifold triangle mesh without boundary, there's a more general version of this, but it's okay, is equal to 2 minus 2 times the genus of your surface, where genus is the number of holes. So here, we always talk about donuts, so I managed to find donuts with different genuses here. So if we look here, this what do they call these things at Dunkin' Donuts? Munchkin, thank you. This munchkin here has genus 0 because there's no holes punched in it. Right? There's one hole punched here. Now the term hole is one that obviously you need to define, being careful in math, but here we're going to work intuitively for now. This is, the problem is this class is doing differential geometry and all this discrete stuff in one. You've got to give something. And then here, this double torus object, which is remarkably hard to find on Google image search, has 2 holes in it, so the genus would be 2. If there's a surface, a boundary, you have to be a little careful how you count the genus. But in any event, there's a beautiful theorem from combinatorial geometry, topology really, that v minus e plus f is always equal to this quantity, which notice doesn't depend on any of these 3 counts. This is a thing that, like, as I take my surface and deform it around, or even change the activity, remains the same. Was there a question here, or was it just an arm motion? Just an arm motion. Okay. So, genus typically tends to be small. This is a generic phrase that you're going to object to. But like in general, we don't maybe work with surfaces that have like a million holes punched into them. And that allows us to make some useful estimates that we are going to derive here. Because there are things that come up a lot in practice. So in particular, we're going to do a terrible physicist like spherical cow kind of thing. I saw these cute t-shirts from Tessa's group. They have like spherical harmonic cows. But in any event, let's do a tiny, so I'm like skipping, Euler's theorem, like the famous interesting stuff, and just doing the boring calculation you can do as a result. But in particular, let's say I have a triangle mesh without boundary, and I want to kind of equate like the number of vertices, the number of edges, the number of faces, just roughly, right? So here's a very simple thing that I can observe. I'm going to say something really profound, which is that every edge on a surface without boundary is adjacent to how many triangles? Every edge is adjacent to how many triangles if there are no boundary? 2, right? 1, 2, yeah, okay. Okay. How many, let's see here. How many edges does a triangle have? That was so slow and quiet. One more time. How many edges do we have on a triangle? Thank you. The people in the back now, just back us. See, that's what I thought. Oh, one more time. I treat you guys like elementary school kids until you wake up. Okay, so in particular, we have this fact, right? That 2 times the number of edges is equal to 3 times the number of faces, right? Because every face has 3 edges. Every edge is adjacent to 2. That makes sense? Okay. So if we then go back to our Euler formula, now we can make a bit of a substitution in the case of closed surface. In particular, here the chi is equal to v. Now maybe instead of e, we say minus 3 half f plus f. Yeah, haven't done anything to extend. Okay, so in particular, what does that mean? That means that this is equal to v minus f over 2, if I did my fractions right. We're nodding, good. I can tell you that this one pays attention. That's good. Okay. So now we're going to do a terrible physicist thing, which we're going to say, okay, v, e, and f are really big numbers, right? Chi tends to be pretty small. So like maybe we say like, okay, so chi is maybe roughly 0. This should make you uncomfortable because it should. Okay, but let's say that that's the case. Okay, so that would imply that, okay, if I reshuffle this formula here, the number of faces is approximately equal, this is now approximate, to what? Well, 2 times the number of vertices. Okay, and these are useful estimates because like roughly when you're doing your like algorithmic thing, and some parts of your algorithm are like in terms of the edges, and some parts in terms of the triangles, and some whatever. It's useful just for accounting to have these estimates in the back of your head. Also, just to remember, like, are there more vertices than faces? Yes, probably by roughly a factor of 2. Okay. So what have we shown so far? We've shown that the number of edges on a mesh without boundary is equal to 3 half times the number of faces, which is roughly equal to 3 times the number of vertices. Yep. I hopefully did that right. Yep, 3 halves and 2 makes 3. With me so far? I promise I'm going somewhere with this. Okay. So let's say that I wanted to compute the average valence of a vertex on a triangle mesh, just roughly on average. So remember what a valence is. It's like the number of edges that go out of a vertex. This whole thing is a vertex, in case you're wondering. OK, so we have average valence equal. OK. Well, we can do a similar argument to what we did up here. Every edge is adjacent to two. Every edge is adjacent to how many vertices? 2. OK. So like if we did average, remember we're summing over all the vertices. Right, so we have kind of like the total number of edges over the total number of vertices. So we have 2 times the number of edges divided by vertices. So hopefully we agree this is the average valence per vertex, because every edge is adjacent to 2 vertices. But conveniently for us, well, we now know that E is approximately 3V. And that leads us to a rule of thumb that computer graphics programs use all the time, which is the following, that the average valence, OK, so that's going to be 6 V divided by V, or 6. Yeah, so this is approximate. This is another cool topological, not quite invariant, because there's a squiggly equal sign here. Which is to say, if I have a very typical triangle mesh, and I take a look at a given vertex, and I look at the edges out of it, chances are that number is 6. And in fact, if you look at your typical subdivision rules, like loop and what's the other one? Catmull-Clark, you'll notice that they tend to, when they're creating triangle meshes, they tend to create valence 6 vertices. And so those have a special name. They're called regular vertices. OK. Oops, and I think that argument's also on the slide. But in any event, there's our argument here. Yes?
Is there a connection here to carbon being a very straight product of pi and stuff? Because it has 6 valence selections. So you could build these meshes, basically.
That's a fascinating question, and one that I wish I were qualified to answer. Yeah. Sorry, but sure, Google it, maybe. Yeah, yes.
The first one works for closed meshes, and the second one is for non-closed meshes.
That's the question. Yeah, the short answer is no. You have to be very careful. If you have a boundary, then the Euler characteristic is kind of annoying to compute. And in fact, it gets worse. Like this is a calculation that people in our research field get wrong all the time, because these topological invariants show up in like this discrete exterior calculus stuff, like when you're doing the size of the null space of a matrix, and whenever there's a boundary, we all screw it up. Actually, I can point you to one of my own research papers where we did this super carefully, and it ended up it gets referenced all the time for that. The actual contribution of the research paper nobody cared about, but the carefully counting dimensions and doing Euler characteristic in that case was something people couldn't find anywhere else. It's not hard. It's just bookkeeping. Yeah. Right, so this is only for closed things without boundary, and notice that like with low genus. I guess for genus 1, like so for tori, these are all equal signs. Yeah. Okay. Right, so what have we done so far? We've defined manifold. The other thing that we need to define is what it means to be orientable. So like here's a Mobius strip triangle mesh. Notice that it's possible. Like sometimes people don't think about it and they think like, oh, you can't triangle mesh a Mobius strip. You certainly can. There it is. But you can't give it a normal field. Notice when we talked about orientability, we talked about like being a smooth field of normals, or at least continuous. Is that probably a good definition for a discrete object like a mesh? Not really, right? Because like, what does smooth mean? I mean, you have this combinatorial object with all these facets. Like, every face, every triangle has a well-defined normal. But like, how do you move one to the next is like engineering. You have to figure out what it means to be smooth, right? And so we need kind of a dual definition here, right? Namely that like, on this kind of object, there just doesn't exist a smooth normal field. You might be able to extend this definition, but you have to do a lot of work to do it. Okay? So instead, do kind of a cute thing here, which is duality between orientability in the normal sense and orientability in the kind of right-hand rule sense. So let's say I have a smooth surface and I have a normal vector. Everybody raise your right hands. Thea can too. Thank you. And now I'm going to grab the normal vector with my hand like that. And that was my experiment. I can my hand along the surface, right? And every time that I drag to a different normal vector's point, notice that I have this direction that my fingers are pointing, which is clockwise or counterclockwise, the direction I'm at. And I can essentially continuously assign a clockwise intersection to every point on my surface, and that is dual to having a normal vector. Yeah? Now, this version of the definition for smooth surfaces is annoying to work out, but it works really well for discrete surfaces. So this is what we're going to do here. Namely, on every triangle, we're going to define like a counterclockwise direction, and then we're going to say a surface is orientable if those directions are compatible. And notice when I assign counterclockwise, that just means an ordering of the three vertices. Does that make sense? Notice, by the way, that if I wanted to compute the normal to the triangle, what would I do? I'd do this minus that, cross product with that minus that. And in doing that, I actually used an ordering of the vertices, like vertex 2 minus vertex 1. And notice, depending on how I order, my normal will flip up or down. So like these definitions are connected to each other. OK. Oops, actually, I guess I don't have anything in those. Right, so in particular, the question is, what does it mean to have compatible orientation for two triangles? So this is a little bit annoying because there are multiple ways to number off the vertices. So here's my triangle mesh. Let's say that I have, to be consistent with my notes here, I have vertices 1, 2, 3, 4. I've got triangle A and triangle B. So for triangle A, give me a counterclockwise ordering of vertices for triangle A, somebody. Anybody? 1, 2, 3. Do I agree with that? Yes. Right? If I traverse 1, 2, 3, counterclockwise, then I get counterclockwise over. Is that the only one, by the way? Somebody give me a different ordering. 2, 3, 1. And a third one. 3, 1, 2. OK. And similarly for B. What was that? So how about 3, 2, 4? Yeah, I think. Hopefully. Yeah. Or 2, 4, 3. I'm tired of waiting for you people. Or 4, 3, 2. OK. So let's take any edge on my triangle. So how about like 2 to 3, like that? And let's look at the connection between 2 and 3 in each of these triangles. What do we notice? It's ordered 2, 3 here. It's ordered 3, 2, and the other guy, right? So one way of figuring out if I orient every triangle by just numbering off the vertices, in some sense that like gives a little arrow to my edge. And essentially what I need to say is for the neighboring triangle, the arrow needs to point the other way. As long as I do that, I have a consistently counterclockwise ordering for all the triangles. Okay? So that's the definition there. Okay, so in the last like 5 minutes of this class, we're going to really quickly talk about data structures, or should I put it off till next time? What do we think? Yeah, you guys are dead and boring, and I'm tired of talking, and this is slow. So we will continue this lecture on Tuesday of next week when you're all going to be much more awake because you're rested for the weekend, and we'll talk about data structure for storing surfaces. Does that sound good? Yes, that sounds great, Justin. I'm so excited for Tuesday's lecture. Thank you so much, and I'm so glad for your enthusiasm. All right, guys, have a fantastic weekend. We will post the homework soon, and I will see you all on Tuesday.